So this is going to be the fourth chapter of the second section of geometry, and this is going to be the start of our proofs. So proofs is kind of a concept in geometry where you have a sort of idea or sort of statement that you want to prove whether it's true or false, essentially. So we're going to kind of go through how to do that with some very beginning basics here before we start amping it up. And this is going to be something that's going to kind of continue on throughout most of first semester and even some of the second semester, these proofs and how to read them, work with them, and what they kind of mean. So, some things before we get started on proofs here. Proofs use, the very basic ones at least, use axioms and postulates. So axioms and postulates are basically the rules of geometry. These are statements that do not need to be proven. They're kind of assumptions that we make. So these are stuff that are kind of self-evident or kind of the given of our current situation. We don't need to prove these because we're going to only work within these systems. We're going to only work with a system where between 2 points there's a line and stuff like that. So axioms and postulates, they both kind of mean the same thing, but these are statements that are assumed to be true without proof. Theorems, on the other hand, are what we're going to use proofs for. So theorems are proved, so they're not assumed, they have to be proven using axioms, postulates, and definitions. Definitions being, like the midpoint is in the middle of 2 points. That's the definition of a midpoint. So that's what we mean by definitions. So for example, all the angles in a triangle add to 180. This can be proven using axioms and postulates. So what are the axioms and postulates? So they're actually Euclid, remember the father of geometry here, actually had, I believe, 5 axioms and postulates. I'm actually a little bit unsure about that right now for some reason. But there's about 5 or so. Here we have a few more. And again, these are numbered this way for this publisher, but not everybody numbers them the same way here. So don't really pay attention to the numbers like 2.1 and 2.2. Pay attention to the ideas or the concepts. I'm not going to talk through all of them because, again, you can read them on your own time. You can pause it and look through it if you want to. But some of the basic ones, like, between any 2 points, there's one line. A line contains at least 2 points, so you need at least 2 points to get a line. If two lines intersect, then there's only 1 point that they intersect at. That sort of thing. So, again, these are self-evident truths that we don't need to prove. Now, algebra also has its own axioms as well. So algebra has some axioms like addition, addition, subtraction, multiplication, division, property of equality. So this was like, when you were doing solving algebraic equations like this. 2x plus 5 equals 9. Well, the first thing you might do is say minus 5 to both sides, and you get 2x equals 4. Well, how do you know you can do that? Well, that is the subtraction property of equality, which basically means you can subtract something from both sides of an equal sign and still keep it equal. That's an axiom of algebra, essentially. And then when you divide by 2 on both sides, you get x equals 2. Well, how do you know that's true? Well, it's because the division property of equality. That says you can divide both sides of an equation by the same number and still keep the equality intact. So these first four are something you've been using, just haven't put a name to them really. These down here are a little bit more nuanced, but you still use them, like substitution property. That means that if I have 2x plus 1 equals 3, and I know, well, let me just not even put the equals here. Let's say I have 2x plus 1. And I also know, let's say from a previous example, I also know that x is equal to 5. Well, this means that I can take out the x and replace it with the 5. So I can do 2 times 5 plus 1. That's what substitution means. You can take out something from a problem and put in something of equal value. Or put another way, if I say 2 plus 3, I can replace that with 2 plus 2 plus 1, because 2 plus 1 is the same as 3. So I can substitute these in for each other and still keep everything equal. So that's what the kind of substitution refers to there. Distribution is about that distribution stuff in algebra. So that means that you have 2 times x plus 1. Distribution says you can take that 2 and multiply it to both numbers and get 2x plus 2. So that's all distribution is, something you probably did in algebra quite a few times. Transitive we talked about in the last video. So transitive is that if A equals C and C equals B, then A equals B. We did that a little bit in the last video, so you can look at that in the last video if you want a little bit more on that. Symmetric means you can flip stuff about the equal sign. So 2 equals 1 plus 1. is the same as 1 plus 1 equals 2. So that's what symmetric means. You can flip stuff about the equal sign. Reflexive comes into play a lot later on, but reflexive basically means something is equal to itself. So A equals A, 5 equals 5, etc. So reflexive simply means something is equal to itself. That's all reflexive is. So let's look at some proofs in algebraic form first before we get to the geometric form. And my mic might cut out here, so again, if I go silent for a minute, just let me reset my mic and I'll be back into it. There are many ways that we can do proofs, flow proof, paragraph proof, but the most common and the way we're going to focus on for this course here is two-column proofs. So we're going to do that no matter what the directions of something say. We're always going to go to a two-column unless otherwise stated, which is not often. So let's go ahead and look at an example of a two-column algebraic proof before we get into the geometric proofs. So two columns are said to be two columns because they have two columns. Proofs start with a given statement, so this is something you know to be true. So 2x plus 6 equals 14. I know that to be true because that is given to me. This is what I want to prove. I want to prove that x is equal to 4. Now, some of you might be able to do this in your head, which is great, but we're going to go through it proof style here. So on one hand here, you have your statements. Yeah, forgive my misspellings there. And on the other hand, you have your reasons. Now, you don't necessarily need to write these each time. Some people just put an S and R, but that's where the two columns come in. You have your statements or what you're doing algebraically here, and then you have your reasons as about why you can do it over here. So your reasons is kind of like why you can do what you did on the left side. So we're going to start with 2x plus 6 equals 14, and my reason is going to be given. This is how you start every two-column proof, especially in the geometric sense, is you always start with just restating your given statement. 2x plus 6 equals 14 because it's given. Okay, so then what can we do? Well, if we're doing it math style, we just subtract 6 from both sides, right? And we get 2x is equal to, let's see here, that would be 8. Now, what's the reason we can do that? Well, over here, we would put subtraction. I'll just put subtraction, property of equality. So POE is short for property of equality. So you can put that at the end if you want to. Now, you don't need to draw this arrow. I'm just doing it to help keep everything nice and in line. But that's how you would go about your proof, is each step would have to be backed up by a reason. So in this next case here, I would divide by 2, and you get x equals 4. Why could you do that? Well, because you have the division. I'll just put the division sign here. Division property of equality. And that'd be the end of it. So if you want to be fancy, some people put QED. You can ask your Latin teacher what that means. It's a Latin acronym for something. Or some people, if you're even fancier, put 3 dots in the form of a triangle. This is kind of an ancient way of saying, the proof is done. This is kind of an old school way of doing it if you want to look fancy. You don't need to, but those two options are there for you if you want to, put a final flair on your proof or whatever. But that's how a proof goes, is you start with your given statement, and then each step you do to get towards your answer, which is what your proof statement is, you have to back up by a reason. So once you get your proof statement in your statements column, then you're done. You just back up that with a reason, and you're good. Let's try one more here. If we can make it go. There we go. So I'll put S and R here. Statements, reasons. We're going to start with our statement, 5 minus 4x equals 21, and our reason is given. And then in this case here, I would subtract 5 from both sides. I get negative 4x is equal to, let's see here, that would be 16. And the reason for that is, again, subtraction, POE. And then I would divide by negative 4, and I get x is equal to negative 4 by, again, division, POE. So actually the same steps as the last one there. Not very. I should have probably switched that up a little bit, but so that would be my proof there. Again, same thing you did last year in algebra, but just backing it up with the reasons each time. And we're going to take this to a more geometric form here shortly. But that's how a two-column proof goes, is you start with your given statement and just take it one step at a time as you work your way towards getting this answer here. So in a sense, they actually tell you the answer. This is the answer to your problem. Now you just need to know how to get there. So let's do this with some geometry here then, okay? So because geometry goes the same format, but it's a little bit different in how you get your reasons there. So here, it says given that P is the midpoint of JK. So here is JK. K, and we know that P is the midpoint, MP. Prove that X is equal to 2. So this is kind of a hybrid algebra geometry proof. What we're going to do here is we're going to use geometry to try to set up an equation, and then once we get that equation, we're going to use our algebra methods to solve it for the rest of the proof. So it says P is the midpoint of JK, and we know that JP is equal to X and PK is equal to 5X minus 8. So this is all given. This is given in the statement, and these two items are given in the actual picture. So this is all given information. So I'm going to put a bar here to kind of separate my steps. Now, if P is the midpoint, this is where the geometry comes in. If P is the midpoint, that means P is in the middle of J and K, which means that JP has to be equal to PK. Whoops, PK. So JP, this segment, has to be congruent or equal to this segment. I'm actually going to put congruent here, and you'll see why in a second. So JP is congruent to PK. Now, how can I back that up? What's my reasoning for knowing that? Well, the reason for knowing that is definition. We'll put DEF, definition of midpoint. Midpoint. Because that's what a midpoint does. A midpoint is in the middle of two segments, and therefore it cuts it in half. So definitions are one of the first ways we kind of use to kind of get proofs started, because definitions kind of show that, okay, this is happening because by reason of its being, by the purpose of its creation, that's what it does. So what's a midpoint's purpose? Well, it's to cut something in half. So if I know that P is the midpoint, I know this segment's been cut in half, so I know that the first half is equal to the second half. And again, why do I know that? Well, because it's a midpoint. So if your first statements, your first few reasonings are usually definitions to get your proof started, and then you go using later stuff on. Especially now when we're just starting proofs, we don't have a lot of other theorems to back up our stuff with, so we're going to rely a lot on definitions to help us out. So definition of midpoint, and again, you're going to use this one a lot. So just kind of make sure you kind of get used to it early on here. Definition of midpoint is used to say that one half of a segment is equal to the other half of a segment. But obviously, you can only use definition of midpoint when you have a midpoint. So it says given P is the midpoint. If they didn't tell us this, we couldn't use definition of midpoint because we wouldn't know it was a midpoint. So we have to be given that something's a midpoint first before we can use the definition. Now, after this comes the common step of change this from congruency to equality, because congruency, remember, means two figures are equal. Equality means two values are equal. And x and 5x minus 8 are value numbers. So what I'm going to do here is, again, this is usually how it goes. There's my cursor. I lost check my cursor there for a second. You say JP with no bar is equal to, not congruent, to PK. So all I do here is swap out the congruency for equality. And this is just definition of congruency, which I usually write using the symbol. So definition of congruency is simply used. What's the purpose of definition of congruency? Simply to change from congruency to equality or vice versa. Now, I usually am not too much of a stickler on this step because usually the only reason of doing this, in fact, the reason that we're doing it here, is so that then we can substitute in the x and the 5x minus 8 for JP and PK. Because this step here means that this segment is congruent to this segment. This step means that this value is equal to this value. It sounds like a trivial difference, and to be honest, it kind of is, but it's that idea of making sure that every step that we go along is accounted for and we're not skipping over any piece no matter how small. So if you want to start putting in your algebra stuff, you have to get things to be equal, and that's when you use definition of congruency, to go from congruency to equality. So now what we do is we say, okay, this is the value of JP. Well, the value of JP is x, so I'm just going to put in x. This is the value of PK. Well, the value of PK is 5x minus 8, so I'm just going to put 5x minus 8. Now, again, we have to back this up. So how can we back this up? Well, this is the substitution. Substitution. POE. POE. Some people just call it substitution. That's fine too. But substitution, remember, allows us to take something and replace it with something of equal value. And I know that x is of equal value because it says right here, JP is equal to x, PK is equal to 5x minus 8. So I can take out these variables, essentially, and replace them with something of equal value. So substitution allows you to replace one thing with another thing as long as they're said or proven earlier to be equal. And then this comes back to the algebra stuff of it. So now I'm back to an algebra proof. So I can just say, all right, I'm going to subtract 5x to get my x's on the same side. So negative 4x is equal to negative 8. I can do that by subtraction, POE. I should probably put bars here, but I'm not, just to make this a little bit easier. And then divide by negative 4, we get x is equal to 2 by division, POE. And that would be the end of the proof. So that would be our triple triangle there, or triple dot, I should say. So that's how a sort of hybrid geometric algebraic proof would go. We use geometry for the first steps to set up an equation, this, and then once we got the equation set up, we use substitution to get it into an algebra form, and then we use our algebra methods to solve it the rest of the way. So that's kind of how these proofs are going to start with in this first few lessons here, is we're going to kind of do an algebra geometry hybrid before going full-blown into just geometry proofs. But again, the two main concepts we're going to be working a lot with here are definition of midpoint and definition of congruency. So these are going to be used a lot this semester and throughout most of the class too, because this is kind of the first way you start proofs, even later on down the line, because it gives you kind of a ground level to work off of. So definition of midpoint and definition of congruency are going to be said a lot in this lesson here, so just be prepared for that. So let's try another one here. This one's actually purely geometric. It's a short one, but it's purely geometric, just to give you a taste about what this is going to look like here. So I'm going to start with my two columns, statement on one side, reason the other. I always start with my given statement. So given, sorry about that, that's where my mic cut out. Let me just make sure it's up and running now. Okay. So I always start with my given statement. To save myself some time on this video, what I'm going to do is do it like this. Do all that, draw an arrow down here, and my reason is given, just so I don't have to write that all out, because as you can see, my handwriting's poor to begin with, and I don't want to mess it up any further. So given that y is the midpoint of xz and that xy is congruent to wy, prove that wy is congruent to yz. So we want to prove that wy is congruent to yz. That's my goal. Now, I like to mark up my diagram with what I know is going to be true and then go to my two column and prove it. So it says y is the midpoint of xz. So over y, I'm just going to put mp. So I know that's the midpoint. And it also says that xy, so this segment right here, is congruent to wy. This segment. So I'm going to mark them as congruent. Because again, it's said in the given, so I can mark it on the picture, just so I have a basis. Well, here's that word again, midpoint. So if they give us that something is a midpoint, that means we're probably going to use definition of midpoint as one of our first steps. So I'm going to write that down here. Definition of midpoint. I'm going to put MP here for short. Definition of midpoint. So again, these first few easier proofs in this lessons here, we're going to always start with definition of midpoint or something along those lines in most cases. I shouldn't say always, but in most cases, we're going to start with that. Now, why do we use definition of midpoint again? Definition of midpoint, if we look back here, is usually used to say that two segments are congruent. That's how we use definition of midpoint, is to say that two halves are congruent. So what are the two halves here that we want to make congruent here? Well, if y is my midpoint, that means my two halves are xy and yz. Those are my two halves. So I'm going to say that xy is congruent to yz by definition of midpoint, because that's what a midpoint does. A midpoint makes two things congruent. Right? So I shouldn't say two things. I should say two halves too, because it doesn't make yw congruent. It makes the two halves that it's in the middle of congruent. So that's definition of midpoint. Now we can actually end it in this next step here, because I want to get wy congruent to yz. And I know that yz is congruent to xy. So if I want to do this here, I know that xy is congruent to wy. So that's part of my given. Xy congruent to wy. So if these two things are congruent, then I can take my xy and replace it with a wy whenever I want by substitution. So I can take this xy and replace it with a wy congruent to yz. Now, again, how do I know that's true? Well, because of substitution. Substitution. Because substitution says I can take something like xy here and replace it with something of equal value like wy. because this was said in my given statement to be congruent. If these two things are congruent, that means they're swappable. So once I have it down here, I can swap it out, and lo and behold, I get exactly what my proof statement is asking me to do. So this would be a QED. This would be done here. So this is kind of an example of a purely geometric proof. You start with a given statement, and for the most part, it's a matter of setting up a link for substitution. This can also be called transitive property here if you want to do that as well, because transitive and substitution are kind of the same thing. But that's how most of these geometric proofs go, is you start with a given statement and you try to construct some sort of link between two segments you want. So I want to connect WY and YZ. I want to connect these two segments here. How do I do that? Well, I use XY as my middleman. So I say, well, WY matches XY and YZ matches XY. Therefore, they have to match each other themselves without XY being a part of it. So again, it's about setting up links that you can then connect together at the end, likely using substitution. So that's it for this video. I'm going to probably put another one up here on just some more proofs, but I don't want to make this one too terribly long because it's kind of a new topic for a lot of you. This is a really new way of thinking. So again, please be patient with yourself if you don't quite understand this right away. It just takes some practice and some time. And in fact, it might not even sink fully in until kind of midway through first semester or even close to the end of first semester. That doesn't mean you're going to struggle and get bad grades or everything. It just means that you're probably not going to get entirely comfortable with it until a little bit later. And think of it as learning how to solve equations again. Proofs are to geometry as solving equations is to algebra. So you probably took a while to learn how to actually solve an equation in algebra like 2x plus 5 equals 10. But once you got the hang of it, it was something that, again, should be pretty much routine by now, solving a basic algebraic equation. Geometry and proofs are just like that. So it's going to take a while to get used to the flow. You're still going to succeed and be able to do it. It's just going to take a while to get used to the idea before you get entirely comfortable with it like you were solving an equation. So that's it for this video. Again, I'll probably put another one up here sooner to go over some just basic proofs here as just a pure example video. So here are some proofs, here are some examples just to give you some more exposure to them. So hopefully this helped you out. Have a good day.